Welcome to the lesson on polar coordinates. This is a very exciting time in your math careers because this is something that's going to come up time and time again in Cal 1, Cal 2, Cal 3, and I think you'll be surprised when it does come up in your later physics classes or whatever science class. So we've got a couple objectives, and first thing is just getting used to the overall coordinate system, and then we're going to transform between the coordinate system that you're used to and this new polar coordinate system. Okay, so I'm going to start with a real quick overview of the goals and show you a picture. We're going to just, in short, understand this new system for graphing, and here's what it looks like. Alright, so let's relate it to things that you know already. Think to yourself, what point 3, -4 means? What does that mean geometrically? And please pause the video and just think about that in a moment and try to respond as if you were talking to someone younger than you. Yeah, I bet you that if you did pause the video and try this, you thought this way. You went over to the right 3 and then down 4, starting at the origin. Okay, well, can you think of any other way to go from this point down to this point that doesn't use left, right, up, down? So consider this instead. I'm actually going to take a length here, and I'm going to go around, or pardon me, on top of the x-axis. So I'm going to go 1, 2, 3, 4, 5, and then I'm going to do something really strange. I'm going to leave this distance fixed, and I'm actually going to swoop and rotate this kind of line segment here until it comes right down here. And I can say that, well, if you want to get from the origin to that blue point down there, you can take a fixed length r and then rotate it a certain number of radians or degrees and then project, or I should say radiate, from the origin to arrive at that point. Well, this is the way that we're going to graph in this polar coordinate system, and before I get really technical about it, I want to share with you the coordinate system that you've already seen. What you've seen so far whenever you see coordinates in terms of x's and y's, that's called Cartesian coordinates. Another thing that you're going to hear me say a lot in this unit, and your future teachers are probably going to say, rectangular coordinates. So they're called rectangular coordinates because, of course, you go on a rectangular grid and you think left, right, up, and down, always going around or on the edges of rectangles or squares. Now, they're called Cartesian coordinates because originally they're supposedly developed by a guy named René Descartes. He's the same person that came up with I think, therefore I am, allegedly. Anyways, this guy was really influential in math and especially analytic geometry. And so that's why we say Descartes Cartesian coordinates. And you probably already know this. X, y means you travel horizontally a certain amount and travel vertically this much. Negative in the xy system just means that you go the opposite of the positive direction. And we always say the positive direction in the x direction is right, positive direction in the y direction is up. Okay, now of course to the brand new thing, polar coordinates. Polar coordinates are in the form r, theta. R represents how far you travel radially, because you can almost think about radiating from the origin, and then you rotate a certain amount. And that's going to land you at one particular point. Now, there's a bit of controversy as to who developed these polar coordinates, but most certainly two of the main figures involved were these guys. I am not going to try to butcher these names, but kind of like you'll see in calculus, the invention of calculus and this particular coordinate system is attributed to two different people, and there's a little bit of controversy as to who actually developed it first, or if at all. Okay. Now, we've seen, hopefully now, this new system and how it works with radiating a distance and then rotating a certain amount, but there's actually some new vocab too. So, whenever you're in the polar coordinate system, you don't typically say the x or y axis, though you can. More in general, you just name one axis, and it's this polar axis. The polar axis you can think about as just the positive side of the x-axis, and that's where you always think about starting for your rotations. Now, also, there's a new word for the origin, and you typically call that the pole. So the pole is at the point 0, 0 still. Oh, pardon that noise. But you just call it something different. So let's actually get some practice graphing some points. So it says, graph the following polar coordinates, be sure to label them. Even though you haven't seen any examples, I challenge you to try these first, then come back to see what I've done. Okay, so this for point A is saying that you radiate 4, so you go out 4, so I'm going to graph that real quick, 1, 2, 3, 4, from the pole, and then I'm going to rotate this 5 pi thirds. So I rotate up until I get to 5 pi thirds, and that will end the point at 1, 2, 3, 4. So here's the point A. Now, that is actually really time consuming, and I'd like to share with you another way to graph these points. You can actually go with the the rotation first, like the angle, and then radiate out from the pole. So let's try B real quick. 7 pi 6. Well, you rotate to 7 pi 6, and we're going to travel out 3. So that's going to be right here is point B. Make sure I fill that in. Okay, now for part C, this is where things get screwy. We're going to look at negatives finally. So 5 pi force is the rotation, so I'll go ahead and go to 5 pi force. I know that's in quadrant 3, so I'll go to right here. This should be 5 pi force, right in between 7 pi 6 and 4 pi thirds. But I've got to radiate out -2. Now, before I say what you should do, just think to yourself, what would you do if it said to radiate by -2? Turns out it actually means that you're going to go in the opposite direction of what you'd expect. So you get this point C here. It's still in the direction of 5 pi force, but if you go the opposite direction, it's going to be for the rotation pi force. Okay, so I've got C now. I'm going to go ahead and erase all this extra work here. Now lastly, I'm going to find D. Now we're going to deal with a negative rotation. This is actually a lot easier, I think, than the negative R value. The negative theta value is just saying that you're going to rotate, but instead of the usual counterclockwise, we're going to rotate clockwise. So negative pi thirds is actually going to get you to 5 pi thirds, and we're going to travel out only 1 from the pole. So there we go. There's the point D. All right. So this is, I know, a really weird system, and the negatives can be really trippy, but as just a real quick review, I usually rotate first and then radiate out. In other words, travel out from the origin along that rotational line. And then, if you have a negative radius, just go in the opposite direction after you've done the other rotation. And then for negative angles, you just rotate clockwise instead of counterclockwise. Okay, so you're probably already thinking about this, but C actually looks like you could get there a different way. Maybe you could get there by using a positive radius instead of negative, because that was kind of frustrating. Well, I'd like you to just consider this. Can you think of a different polar way to arrive at this point at 4, pi halves? Please pause the video and think about that first. Yeah, I bet you that you could get to the same point if instead of rotating by pi halves, you could rotate by -3 pi halves. And you could still travel up 4 to get to that same spot. So I can write this real quick. Another point to get you the exact same location would be R is 4 and theta is -3 pi halves. Now, are there any more? Most certainly. You could actually rotate more than 2 pi, and you could do 1 rotation. So think about rotating all the way around to 2 pi, and then rotating another pi halves. Let's see what I get. 2 pi plus pi halves would be 5 pi halves. Make sure I'm not crazy, pardon me. So 2 pi, which would be 4 pi halves plus pi halves, yeah, 5 pi halves. And this would be the exact same location. Now, there's an infinite number more, and in fact, what I'm trying to share with you here is a really important statement, and it's that polar coordinates are not unique. Rectangular coordinates most certainly are, but polar coordinates, there's a ton of ways to get to the exact same location. Now, I don't want it to be misunderstood here. These rotations are most certainly different, especially if you're talking in physics or later in your calculus career. But for just right now, imagine that they're going to end at the exact same spot. You can almost think about that they're coterminal. Okay, well, let's see some examples. This says plot the point P with these polar coordinates and find the other polar coordinates r, theta of this same point for which these conditions are met. r has to be positive, and theta has to be between 2 pi and 4 pi. I challenge you to pause this video and try this one on your own first. Okay, so I'm going to first of all plot that point just real quick. I'm going to go out to pi 6 in rotation and travel out 3. Okay, so now what I'm going to do is find a whole nother point, a whole nother rotation that gets me that exact same point. So it already says that r has to be positive, so I'm going to still use the radius of 3. But now the angle has to be between 2 pi and 4 pi, which is of course more than just one rotation. So the way I'm going to figure this out is take 2 pi and add pi 6 to it. The reason why I'm doing that is graphically, I know that if I go out to pi 6 and then add another 2 pi, it's going to land me at the exact same spot. Those are coterminal. And if I do this, I'm going to get 13 pi 6. So lastly, I get to include that this point is the point 3 comma 13 pi 6. So this is an okay answer for me. I got to tell you, by the way, that later in this lesson, when we start dealing with x's, y's, r's, and theta, it might be a good idea to start getting used to this convention. We actually write out that this is a polar point r comma theta. Okay, let's do the same thing, but it's going to be a different condition. So same point, but now it says that my r value has to be negative, and the theta value can actually just still be between 0 and 2 pi. Okay, so what I'm going to do is first of all plot that point again so I can visualize what's happening. So I'm going to go out to pi 6, then I'm going to go radiate out 3. I get that point. But now I need to get to that exact same point but using a negative radius. Well, here's how I'm going to do that. I'm going to travel in the opposite direction on the other side of the pole. And if I do that, you can think about that pi 6 is 7 pi 6 equivalent in the quadrant 3. So I'm going to say for sure that that point is going to be gotten by rotating 7 pi 6, but in order to get to the original point 3 comma pi 6, I've now got to use a negative radius. So there's my point. And as I mentioned just a second ago, you can also include r comma theta, but I'm not going to yet because there's no x's and y's given. Okay, let's try part C. Same thing, but now the condition is that r is positive, but at the same time our angles have to be between negative 2 pi and 0. I challenge you to pause this video again and please try it on your own first. Well, the radius is going to be positive, so that's good. I already know it's 3. However, for this angle, I know that I'm trying to get to pi 6 and travel out 3. Now, to get that by a negative rotation, I'm going to think taking the polar axis here, and I'm going to rotate negatively. So to figure out exactly what that value would be, I'm actually going to take pi 6 minus 2 pi. And by the way, the answer is already given. It's going to be 11 pi 6, which is negative here, but let's just say we didn't know that. And you would combine these by doing pi 6 minus 12 pi 6, and lo and behold, 11 pi 6. Oops, but negative. So the point is 3 comma negative 11 pi 6. And again, you can say r comma theta, and I'm going to be a little bit lazy here and not do that. Alright, so let's now think about one more thing before I move on to the next video. We're going to now superimpose the xy coordinate system onto this polar system and see if we can see some correlation. So I want you to consider the question, what's the rectangular version of 4 comma pi 12ths? It's graphed right here. So you travel or rotate pi halves and then radiate out 4. And if you were to put that on the xy grid, it'd be this point. What's that point? Yeah, it turns out that this is strange. The x value is 0 and the y value is 4, which can be really confusing because we got 4 pi halves and the 4 is on the left, but then 0 comma 4 and the 4 is on the right. Well, this is where it becomes super duper important that we start including x's and y's whenever we indicate this stuff. So for the rest of this lesson, you're going to see me do stuff like this is the point x comma y, and this is the point r comma theta. Okay, well that is it for this video. At this time, please move on to the next video for this lesson.